Today we're going to determine the number of valence electrons for any atom and write its Lewis symbol. We'll apply the octet rule to the arrangement of electrons in the valence shell for an atom, and we'll be able to explain the significance of electronegativity and relate the electronegativity of an element to its position in the periodic table. So first we have to look at the different types of chemical bonding, and then we'll look at something called lattice energy, and we'll talk about electronegativity and bond polarity. The quest that goes with this is types of bonding. So a lot of this will be review. The first thing when we come to talk about bonding is the three different bond types. The main two we're going to focus on are ionic and covalent, but do know that metallic bonding is also something that occurs, and we'll talk about that momentarily. Covalent's the huge focus of this chapter. We've talked about ionic previously, but covalent's really important because it helps us explain our interactions between different molecules, and we start getting into intermolecular forces, which is a unit that will be coming up shortly after this one. When we're talking intermolecular forces, we have to look at things that are polar and nonpolar, and then we start talking about dipole-dipole interactions, hydrogen bonding, and London dispersion. Those things won't be covered in this chapter, but like I said, they will be coming shortly. When we think about chemical bonds are forces of attraction that hold groups of atoms together within a molecule or a crystal lattice, and it makes them function as a unit. When we think about that, it is good to think about Coulomb's law. So we've got Coulomb's law, which we looked at briefly in the last unit. The equation for that is the energy is equal to 2.31 times 10 to the 19th joules times nanometers, and that is times Q1 times Q2 over R. Q1 and Q2 are the charges of your anions. So those are your charges. And R is the radius, the distance between the two ions. We primarily use this for determining the attractive force between ions. You don't see this particular law when it comes to covalent. So this is for ionic compounds. If you think about the amount of positive charge, the effective nuclear charge, this law makes a lot of sense as the amount of positive charge between the two nuclei increases, and the amount of negative charge increases, then we start to get a greater sense of attraction. So actually, let's look at that in terms of our internuclear distance. There's a great atomic interaction simulation on PhET. And so with that, there's an optimal distance when things bond together that allows things to be at a stable energy. If we think about it, when you have two atoms coming together, there are two forces at play. And actually, I'll go back and write those. The first force, you've got repulsion between nuclei, right? Because you've got positive charges there. So positive and positive. We also have the repulsion between the electron clouds, negative and negative of the electron cloud. And then the third thing that comes into play is our attraction between our positive nucleus and our electrons. So when we go back to that simulation and we look at this graph, it makes sense. As I click and drag this, you see it starts to move. There's attraction there, but the minute they get too close, they repel too much and they move away from each other. You'll see that the closer they get, there's this kind of optimal distance. They keep bouncing back and forth, and there's an optimal distance between them. So as they get too close, you got that overlap, and now you've got electron repulsion. You can see that if you look at the attractive force. You can see the attractive force gets greater as they move together, but you also have a certain electron overlap that makes things too repulsive. And when we look at the energy, there needs to be an optimal energy or an optimal distance at which we have a minimal amount of energy, a minimal amount of repulsion, and a perfect amount of attraction. So it's a constant balance. We can look at this. You see that here the other important thing is that the attractive force is equal to the repulsive force. If we look at something like oxygen, which is diatomic, this one, I'll have to zoom out. If you think about diatomic molecules, we know things like oxygen only exist as diatomic, and that's because the overlap of the electron clouds and the amount of positive charge, it's a very large force. And as I start to move these things away and decrease that force, we're no longer at a minimum energy here. And it's very strange because there's a perfect balance between the two. And you see that that minimum energy is so low that we have a very large attractive force and a very large repulsive force, but they cancel each other out. These things have to stick together this way because this is the lowest possible energy. If we're not in our lowest energy state, it's not going to go very well. Okay. If we looked at things that are larger, I like this one. I'll have to zoom in a little bit. You see there is a minimum amount of energy there. This is argon and neon. So size may affect things a little bit, but we're really looking at just the repulsions. This is area of where it's just right. When things are too far, you still have a little bit of attraction, but when we're out here, that thing's not moving. It takes a lot to make that thing move closer. And if it's out here, it's not really going to move at all. It's too far away. You're not really going to get much attraction between the two. Okay. All right. So when we're looking at ionic substances, there's a lot of characteristics we have to look at. We know that in an ionic compound, electrons are transferred between atoms. They also have high differences in electronegativity. We're going to talk about electronegativity difference shortly, and we're going to look at the Pauling table of electronegativity values. Memorize that number, 1.67. When the difference is greater than 1.67, it is going to be considered ionic. We also know ionic compounds are metal and non-metal, so things like salts, like table salt. Sodium is a metal, chlorine is a non-metal. There are strong electrostatic attractions between positive and negative ions, which then leads it to form that network, that kind of crystalline structure that we see. We'll show you the lattice structure of NaCl on the next page, or maybe it was lithium fluoride, I forget, but we'll look at lattice structure and the crystalline structure of those compounds. The formulas are given in the simplest ratio of elements, but know that they exist in that crystalline structure. So when we're looking at NaCl, it's not just one NaCl, it's really a whole network of them, where you've got NaCl, Na, and then a Cl, and you can just keep going and going until all these things are connected. It just keeps forming this network, this lattice, per se. Because of their strong electrostatic attractions, they have high melting points. It takes quite a bit of energy to break them off of their lattice. And they're also good conductors of electricity when they're in the molten or dissolved state. When they're dissolved, they have ions. They exist in their ion form, so Na plus and Cl minus. Of course, salt and salt water, that's why salt water can conduct electricity, whereas pure water that doesn't have any ions dissolved in it cannot. When we're talking covalent compounds, these have the sharing of electrons between atoms. They have small electronegativity differences, usually less than 1.67. This is when we have nonmetals and nonmetals together. And when you look at them, they are in the true ratios of atoms. Those are your molecular formulas. Whereas with the ionic compounds, we have a formula unit. So if you hear formula unit, we're talking ionic. If you hear molecular formula, we're talking covalent. These can exist in any state of matter at room temperature, solid, liquid, or gas, and they typically melt at low temperatures, and they do not conduct electricity very well. Like I said, the bulk of this unit is dealing with covalent. One other thing we have to look at is there's subcategories of covalent, that's polar and nonpolar. We'll look at that when we get to our electronegativity values. So metallic, this is one we won't spend a lot of time on, but it's good to know. Metallic substances, obviously looking at the root, these are metals. If you take a chunk of copper per se, you can hold a chunk of copper in your hand. We know copper is a good conductor, but we don't really know how those atoms are stuck together. What happens is we end up getting a network of these atoms, and there's a sea of mobile or delocalized electrons that surround your positively charged metal center. So since there is an attraction between the metal ions and the surrounding electrons, and they're mobile electrons, they can conduct electricity, because if you were to shoot, I don't know, say, shoot an electron towards a conductor like this, it could dislodge or collide with other electrons in that sea and then cause them to move forward. And then it's kind of like a domino effect. If you hit one electron out of place, then it's going to move to the next one, and then you end up getting your flow of electrons in that regard. They are still a crystalline structure, as I said, but when we write the formula, even though it is around a positively charged metal, we write them as neutral atoms because it's a network of them. Okay. They also have a range of melting points, and it typically depends on the number of valence electrons. Okay, lattice energy. So lattice energy is the amount of energy it takes to separate a mole of an ionic solid into its gaseous ions. So if we look at potassium chloride, and we wanted to separate a solid potassium chloride crystal into K plus and Cl minus, the energy associated with that would be the lattice energy. You'll notice that here we've got a 1 plus and a 1 minus charge, and it's only about 701 kilojoules. But then when we look at magnesium oxide, 2 plus and 2 minus, it's almost 4 times that. Actually, probably 5 times that in terms of energy. So as the amount of positive charge, the separation of charge goes up, think about it like a number line. So if you have like, here's 0, 1, 2, 3, 1, 2, -1, -2. As that separation of charge goes up, the more energy we need to separate those ions. And that's where Coulomb's law comes back into play, as we talked about earlier. So when we're talking lattice energy, again, we're looking at things in a crystal. Dang, I thought I put pictures of the crystal in here. So let's look at one. Let's see. So the crystal structure of sodium chloride, this is what it would look like. Something similar to this. Actually, this is a good picture. You've got this network of alternating sodiums and chlorines in their ion form, and when they arrange themselves in this way, we get a cubic shape. Not all crystal structures are cubic. We will look at different crystal structures later, but it is important to know it's an alternating network. We're looking at, in terms of separating a sodium and a chlorine in that crystal structure, that would be our lattice energy. How easy is it to break those things apart from each other? Okay, so electronegativity and bond polarity. Here is Linus Pauling's electronegativity table. When something is more electronegative, as we talked about previously, it's the ability for it to gain or accept an electron. It's attraction for an electron. When we are using this table, we're primarily going to be using it to figure out our bond polarity. As we said before, ionic, The difference for ionic is when it's greater than 1.67. For covalent, it's going to be less than 1.67. And we're also going to look at the subcategory of polar versus nonpolar. If it's less than 0.4, it's going to be nonpolar. So you'll have this range of polar and nonpolar, which is 0.4 to, I'm going to say X for that, 0.4 and then 1.67. Okay? So that will be our range for polar and nonpolar. So we want to order the following bonds according to their polarity. Well, we need to look up the values for each. So H is 2.1. So electronegativity difference, you subtract them. 2.1 minus 2.1 is obviously 0. That is definitely going to be nonpolar. Okay. With OH, you're going to have 3.5 minus 2.1, which is going to equal 1.4, which is going to be polar covalent. It is less than 1.67, but still greater than 0.4. Then we have Cl and H, which is going to be, let's see, Cl is 3.0, so 3.0 minus 2.1, this is going to be 0.9, which is polar covalent. And then let's keep going. So SH is 2.5 minus 2.1. This is exactly 0.4. So that one, you could probably make an argument for that being nonpolar. It's right on the line there. It's not greater than, so you could say greater than equal to. Probably safe bet that's not nonpolar. And then HF, we've got 4.0 minus 2.1. This is going to be 1.9. This is actually ionic. All right. So now we have to arrange them in according to polarity. So let's go, it doesn't say least to greatest, but let's do least to greatest. So we've got our least, and then I think 0.4 is the next one, so SH. Then we've got the CLH bond, and then we got OH. Boop. And then we've got HF, okay, from least to greatest. So electronegativity difference, when we look at bond polarity, it's just subtract the two numbers. We're looking at molecule polarity a little bit later. It's going to have a factor, electronegativity difference, but it's not going to be the only thing that contributes to polarity. And we'll talk about why once we get into 3D shapes. All right. The last little thing I want to make sure we can do, looking at covalent, is drawing some Lewis structures. Just a quick recap. When we're looking at covalent compounds, we want to be able to look at the periodic table and figure out our valence electrons. So when we come over to group 13, everything there has 3 valence electrons, 14 is 4 valence electrons, 15 is 5, and you just go 6, 7, 8, etc. So hopefully that's pretty straightforward. Let's say we want to draw a Lewis dot structure for nitrogen. Nitrogen is in group 15. It has 5 valence electrons. So I've got my 5 dots. If my pen will cooperate with me. 1, 2, 3, 4, and then 5. When you're drawing a single atom, make sure that the dots only pair once you have all the other dots in each of the cardinal places. So if you're like there's a box around it, you should have one in each side of the box before you start pairing up. Say we had something like sulfur. It's got 6. 1, 2, 3, 4, 5, 6. Just like that. Okay. So hopefully that goes pretty easy. When we come back together, the next play posit will be on Lewis structures for covalent compounds. Okay. Have a great day.